Python is the most popular programming language in the world. Almost nobody uses it well. Python is the language everyone learns. It's the first language for data scientists, the default language for ML engineers, the lingua franca of automation, scripting, backend development, research, and AI. It has the lowest barrier to entry of any serious programming language. And that low barrier is the problem because Python is easy to learn and genuinely hard to master. The distance between someone who can write Python and someone who can write Python well at scale under pressure for systems that other people have to maintain that distance is measured in years, sometimes a decade, sometimes more. I talked to 20 engineers, 1 year in writing their first real Python beyond tutorials, 5 years in having their first real opinion about how Python should be written, 10 years in having built and broken things at scale and rebuilt them, 20 years in having watched Python evolve from a scripting language into the backbone of global AI infrastructure, and having strong feelings about almost all of it. I asked all 20 of them one question: what does Python mastery look like? And when did you realize you weren't there yet? Every single answer was different, and every single answer was useful. Whether you wrote your first Python script last year and want to know what good looks like, or you've been writing Python for 5 years and you are not sure if you are growing, or you are a senior Python engineer wondering. By the end of this video, you will have the clearest map of the Python engineering career that exists anywhere on the internet. Across 20 years, 6 phases, 20 engineers. Let's go. This series is unusual and I want to be upfront about why. Most technical career series cover 5 or 7 years of experience. This one covers 20 because Python is one of the few languages where the 20-year engineer and the 2-year engineer are often working in the same code base, and the gap between them is not just experience, it's a different relationship with the language. So this is for you. If you are asking any of these, I know Python syntax. How do I learn to engineer in Python? I've been writing Python for 3 years. Am I intermediate or am I just comfortable? What is different about how a staff Python engineer writes code versus a mid-level one? I work in Python, but my background is data science. Is there a different Python for software engineering, and how do I learn it? What does Python look like at year 10, at year 15? Is there still growth after senior? Python keeps evolving. Type hints, async, pattern matching, Python 3.12 improvements. How do I keep up without getting distracted? This is not a Python tutorial. I am not explaining list comprehensions or how to use pandas. This is something more rare. 20 engineers telling you in order what Python mastery costs and what it gives you. Before we get into the roadmap, I want to explain something about Python that shapes everything else in this series. Python is not one career, it's 5 careers wearing the same syntax. Python for web engineering, Django, fast API Flask, building APIs, services, backends that run at scale. The Python engineer here cares about request handling, database query optimization, deployment architecture, and async performance. Python for data engineering, Spark, dbt, pandas, Airflow, building the pipelines that move, clean, and transform data. The Python engineer here cares about memory efficiency, distributed computation, pipeline reliability, and schema management. Python for machine learning and AI PyTorch, TensorFlow, scikit-learn, Hugging Face. The Python engineer here cares about numerical computing, GPU utilization, training pipeline design, and model lifecycle management. Python for automation and scripting, the glue that holds infrastructure together. The Python engineer here cares about reliability, idempotency, cross-system integration, and the code that runs unattended at 3 a.m. and doesn't break. Python for systems and platform engineering, the deep end. The Python engineer here cares about CPython internals, the GIL, memory management, C extensions, and making Python do things it wasn't obviously designed to do fast. The career arc we are mapping spans all five. And while most engineers specialize, the engineers who reach the top of this language year 15, year 20 have developed enough fluency across domains to move between them without starting from scratch. That breadth, built on top of real depth in at least one domain, is what Python mastery looks like from the outside. This is the longest roadmap section in the series, Give It Room. Here's what I learned across 20 interviews. The Python engineering career doesn't have 4 phases. It has 6, and each one requires something the previous phase didn't prepare you for. This is the phase where Python is still a mystery wrapped in familiarity. You can write code that works. What you can't do yet is write code that someone else can maintain. You discover, usually painfully, that there's a difference between code that runs and code that is good. The first year is largely about closing the gap between what the language can do and what you need it to do in a professional context. You write your first module that someone else has to import. You push your first PR and get comments on things you thought were fine. You debug someone else's code for the first time, code that makes no sense to you, and eventually understand it slowly. The skills that matter here: Python fundamentals, but properly, not just syntax. Understanding mutability, scope, namespaces, how the import system works, writing functions that do one thing, naming variables like you'll read them in 6 months. Virtual environments, pip, requirements files, the basic toolkit of real Python work. Git with a team, not just a version control, collaborative version control. Reading error tracebacks without panic. This skill alone separates people faster than anything. What people think matters in year 1, but doesn't yet. Decorators, meta classes, async, await, the GIL. These are real and we'll get to them, but year 1 is not the time. The engineers who try to learn advanced Python before they're solid on intermediate Python build a confidence that cracks under real pressure. Salary in this phase $65,000 to $100,000 USD. US entry-level Python roles with strong fundamentals 85-1.5K. India, UK, EU, Southeast Asia 35 to 60% variance with cost of living. Python is one of the more accessible first languages, entry-level market depth. The goal in year 1 is not to be impressive. The goal is to be reliable, to be the engineer whose code does what they said it would do, doesn't break quietly, and can be read by a human. That bar is lower than you think, and cleared by fewer year 1 engineers than you'd expect. This is the phase where Python stops feeling like a foreign language and starts feeling like a tool you control. It's also, and this is the part nobody warns you about, the phase where you discover how much Python you don't know. Because in year 2, you start encountering the language's depth, not the syntax depth, the design depth. You write your first decorator and understand what it's doing. You hit a performance problem and learn that Python is slow in specific predictable ways and fast when where to push. You start reading other people's Python, good Python, not tutorial Python, and realize you've been doing things the long way. The skills that accelerate this phase: object oriented design, not just classes, but when to use them and when not to, Pythonic idioms, list comprehensions, generators, context managers, not as tricks, as tools that make intent legible, error handling, not just try, except everywhere, designing exception hierarchies, knowing when to catch, when to erase, when to let it propagate, testing, PyTest, fixtures, mocking, writing code that can be tested, because untestable code is a design smell, not a testing problem. Package structure, how a real Python project is organized, not a single script, a project with modules, packages, configuration, and an entry point. This is also the phase where your domain specialization starts to crystallize. Web, data, ML, systems. The engineers who grow fastest here are the ones who go deep in one domain while staying curious about the others. Salary $100,000 to $145,000 USD. Strong Python engineers with web or data specialization. 130-155K at mid-level. Senior Python is where most engineers plateau and most don't realize it, because by year 5 you feel proficient. The code you write works. Your peers respect your PRs. You've shipped things to production and kept them running. What you often don't know at year 5 is what great Python looks like at scale. Great Python is not clever Python. It's Python that expresses intent so clearly that the next engineer, the one who reads this code in 2 years when you're gone, can understand what it does and why without asking anyone. The skills that define this phase: advanced type annotations, not just type hints for IDE support, full type coverage that makes Mypy happy and makes interfaces legible to collaborators, understanding protocol, type var, generic, and when static typing is a design tool versus when it's bureaucracy. Concurrency and async properly. Asyncio, event loops, the difference between concurrency and parallelism in Python. Why the GIL matters for CPU bound work and why it doesn't matter for IO bound work. Threading, multiprocessing, concurrent dot features. Knowing which to reach for and why. Performance profiling, cprofile, line profiler, memory profiler, finding the real bottleneck instead of optimizing the wrong thing. API and library design, writing Python that other engineers use. Understanding that the hardest part of a library is not what it does, it's how it makes the caller feel. The API is the product. One senior engineer said something I think about often. Year 1, Python, and year 8. Python can look identical on the surface. Both use functions. Both use classes. Both use imports. The difference is in every decision that's invisible in the code itself. Why this abstraction? Why this boundary? Why this name? Those invisible decisions are what senior engineers see that junior engineers don't. Salary $145,000 to $200,000 USD. Python specialists in ML infrastructure, platform engineering, or senior web backend. 190 to 230K at top of market. This is the phase most Python engineers never reach. Not because they lack the technical skills, because they never make the mindset shift that this phase requires. The shift is this: at senior, you own your code. At staff, you own the code base. Not the whole code base, but the patterns, the conventions, the decisions that ripple through it. You are the one who decides, should we use Data classes are pedantic here. How do we handle configuration across 12 services? What does our exception hierarchy look like at the organizational level? When we onboard a new Python engineer, what does idiomatic Python mean for us? These decisions are architectural in the same way that database schema decisions are architectural. They constrain everything downstream, and unlike database migrations, bad Python architecture decisions are invisible until they cost a team months of refactoring time. The skills that emerge in this phase: large scale refactoring judgment, knowing when to refactor, when to rewrite, and when to live with it. That third option, the decision to not refactor, is the hardest and the most often right. Dependency management at scale, virtual environments, lock files, monorepo strategies, making Python dependency hell navigable for a team of 30, not just yourself. CPython internals awareness, not deep kernel level knowledge, but enough to understand what the interpreter is doing with your code, how objects are laid out in memory, why certain patterns are fast and others aren't, what the GIL prevents and what it doesn't. Cross-language interop, Python, C-types, CFE, pbind 11. Because at staff level, sometimes the right answer is this part shouldn't be Python. Knowing when to reach for C extensions or Rust bindings and when it's premature optimization. Salary $195,000 to $270,000 USD. Staff Python engineers at AI infrastructure companies, large scale platform teams, 250 320K plus. At this level, the relationship with Python changes in a way that's hard to describe until you've experienced it. You stop thinking about Python features. You start thinking about Python as a design medium. The question is no longer, how do I do this in Python? The question is, should this be in Python at all? And if yes, what does the Python expression of this idea look like that will serve the team well for the next 5 years? The engineers at this level are usually the ones who define what Python means inside their org. They write the internal style guide, they make the call on when to adopt new Python versions and when to wait. They evaluate new libraries and frameworks, not for their technical merit alone, but for their maintenance trajectory, their community health, and the cognitive load they add to the team. They are also increasingly the engineers that other engineers cite as influences. The people whose code appears in examples, whose opinions get referenced in PR comments, whose decisions live in code bases for years after they've moved on. This professional legacy is unusual in engineering. Python, being the language of so many domains, gives the people who master it a specific reach that single domain languages don't. Salary $240,000 to $360,000 USD total compensation. At top AI infrastructure companies, Google, Meta, or well-funded Python-heavy startups, 350 for 50K with equity. There are very few engineers at this level, and almost all of them would resist the label. But they exist, and their work is worth understanding even if you never reach it, because it tells you something important about what Python mastery looks like at its fullest expression. At 20 years of Python, the engineers I talk to are contributing to CPython itself, authoring PEPs, building the libraries that the rest of the Python ecosystem depends on, mentoring the generation of engineers who will be the next decade's staff and principal engineers, defining the shape of Python communities globally, PyCon, PSF, regional user groups. Their relationship with Python is not transactional anymore. They are not using Python to accomplish something else. They are contributing to what Python is. That is a different relationship with a programming language than most engineers ever develop with any tool. And it doesn't happen through ambition. It happens through genuine, sustained love for a language that has kept growing, kept surprising, and kept mattering for more than 3 decades. Salary at this level $300,000 to $500,000 plus USD total compensation. The engineers at this level often have significant equity, advisory roles, consulting arrangements, and speaking income that makes base salary a smaller fraction of their total earnings than at any earlier phase. This is a 20-year table, widest in the series. Let me put the full 20-year salary picture on the table. This is the most complete version of this data I could build from 20 interviews and extensive job market research. It is a range, not a guarantee. Your domain, your location, and your company stage all matter. Or phase, or VOE, or level, or base, USD, or total comp, or reality check, or functional, or 02 wires, or junior Python, young, or 65K, 100K, or 70K, 115K, or domain focus starts here. Web data, ML, each pay differently, or comp. Advisory consulting, reshape total compensation, or 3 things worth understanding about the Python compensation picture specifically. First, Python is the language of the highest paying domain in technology right now. AI and ML infrastructure. The engineers writing the Python that trains and serves frontier models that Python is running on billion-dollar compute budgets. Python engineers who combined language depth with domain expertise in AI are at the top of the comp curve for any software engineering role. The intersection of Python mastery and AI infrastructure is the highest leverage career position in the language right now. Second, the Python salary curve is longer and flatter than most languages. Because Python spans so many domains, the seniority curve doesn't compress as fast as in specialized languages. A 10-year Python engineer still has meaningful growth ahead in depth, in domain, and in compensation, in a way that isn't always true for more specialized stacks. That's a feature of the language, not a bug. Third, geography matters less for Python than almost any other language. The open source Python ecosystem is global. The AI Python ecosystem is global. The remote hiring market for strong Python engineers is more global than any other language market I've tracked. If you are building real Python depth anywhere in the world, you are building toward one of the most portable and globally demanded technical skills that exists right now. Python engineers want specifics. Give them specifics. Let me talk about skills, and I'm going to be more specific here than I've been in any previous series, because Python has a specific technical depth curve that I want to map as precisely as I can. There are things that separate a 2-year Python engineer from a 5-year one. Different things that separate a 5-year from a 10-year, and different things again that separate a 10-year from a 20-year. Let me walk through all of it. Year 2, the foundations. What knowing Python means. Most people who say they know Python mean they know the syntax. Here's what knowing Python requires in year 1 and 2. The data model dunder methods. What init, reaper, str, EQ, hash do, and when to implement them. Understanding the Python data model is the difference between using Python objects and designing them. Scope and namespaces, Legby rule. What global and non-local mean. Why mutating a global is a code smell. The import system, not just how to import, how Python finds modules. what initPy does, relative versus absolute imports, circular imports and why they happen, mutability, why defx is a trap, why dict is a reference, why strings are immutable, and what that means for string manipulation at scale, comprehensions and generators. Not just list comprehensions, dict comprehensions, set comprehensions, generator expressions, understanding when a generator is better than a list and why, exception handling beyond accept exception, custom exception classes, the difference between except else, finally. Not using exceptions for flow control, the habit that compounds everything in year 1, reading the source code of libraries you use, not the documentation, the source, seeing how real Python is written by people who care about it is the fastest way to develop taste. Year 2 to 5, the intermediate depth where most engineers plateau. This is where Python starts revealing its real depth and where most engineers stop digging. Decorators implemented from scratch, understanding closures first, then functools.wraps, then decorators with arguments, then class-based decorators, then understanding which of these you need and when. Context managers. Enter and exit. The context-lib module. Why context-lib.contextManager exists and when it's better than the class form. Descriptors. What happens when you access an attribute in Python? Properties are descriptors. Understanding the descriptor protocol unlocks understanding of the entire ORM pattern. Meta classes when you need them, rarely, and what they do a lot, not as magic tricks as tools for framework design. Abstract base classes, ABC, abstract method, how the Python standard library uses them, when to use protocol instead, and why protocol is often better in modern Python. Iterators and iterables, iter. Next, stop iteration, infinite iterators, chaining iter tools. Writing memory efficient code that processes data without loading it all at once. The testing depth that separates year 2 from year 5. Not just writing tests that are fast, isolated, and catch regressions. Understanding fixtures, parameterize, monkey patching, the difference between unit tests, integration tests, and why both matter. Test-driven development, not as dogma, but as a design tool. Year 5-8, the senior layer. Python as a design medium. This is where the language stops being something you use and starts being something you think in. Type system mastery. Generic, type for, protocol, literal, typed dict, param-spec, concatenate, understanding covariance and contravariance. Using Mypy or pwrite in strict mode and writing code that passes without gigger type. Ignore. The engineers who can design with the type system write AP is that are hard to misuse. Async Python properly. Asyncio event loop internals. The difference between asyncio.gather, asyncio.wait, asyncio.create task. Handling backpressure. Avoiding the common patterns that make async Python slower than sync. Async generators. Async context managers. And the judgment to know when async is not the answer. Python memory model, reference counting, the cycle collector, GC module. Sysget size of versus actual memory footprint. Using slots to reduce object size. Understanding memory, profiling, not just why code is slow, but why it uses too much memory. C extension interaction types for calling C libraries. CFI, understanding the CPython, CA, PA at a surface level. Knowing when a NumPy array is a C array with a Python wrapper and what that means for performance. Performance profiling discipline. C profile for CPU, memory profiler for memory, PySpy for production. The discipline of measuring before optimizing. And the wisdom to know when the optimization isn't worth the complexity it adds. Year 8 to 12, the staff layer, Python at organizational scale. At this level, the technical skills are not the hard part. The hard part is applying them in the context of a real organization with real constraints. Code base level design, not module design. System design in Python. How services communicate, how configuration flows, how errors propagate and get logged and get alertable. Dependency governance, making decisions about which third-party libraries the organization adopts and which ones it avoids. Understanding library maintenance signals. The difference between a library that is stable because it's finished and a library that is stable because it's abandoned. Python version strategy, when to upgrade, how to manage the migration, what breaks, how to test it across a large code base. Being the engineer who makes Python 3.11 to Python 3.12 a smooth migration for 50 engineers requires skills that no tutorial covers. Internal tooling and toolchain design, the makefile, the CI pipeline, the pre-commit hooks, the internal linting rules, the type checking configuration. The engineers who design these well save hundreds of engineering hours. The engineers who design them poorly create invisible friction that slows everyone down. Year 12-20, the language layer, Python as a craft. At this level, the skills are harder to name because they're harder to teach. Conceptual clarity, the ability to look at a complex Python design problem and find the simple underlying structure that resolves it. Not clever Python, obvious Python. Python that makes the next engineer say, of course. Community and ecosystem judgment, knowing which PEPs to follow, which to ignore, and which ones are going to reshape how Python gets written in 3 years. Reading the Python Steering Council discussions and understanding what they mean for the code you're writing today. Language evolution, tracking structural pattern matching. Python 3.10, exception groups, Python 3.11, fine-grained error messages, Python 3.11, faster CPython, Python 3.11, Python 3.12, P. The engineers at year 15 and 20 are the ones who understand not just what changed, but why what problem was being solved, what trade-offs were made, and what it means for the ecosystem. 20-year Python engineer told me something I haven't stopped thinking about. The best Python I write now is the Python I would have written in year 3, but for a completely different reason. In year 3, I wrote simple code because I didn't know better. Now, I write simple code because I've learned that simple is the hardest thing to do right and the most valuable thing you can give the person who reads it next. There are 6 per phase. Now, I want to walk through. Every engineer I talked to described a specific shift in how they thought about Python. Not what they knew, but how they related to it. 6 shifts, 1 per phase, year 0-2. I need Python to do what I want. This is the orientation of every engineer in their first 2 years. Python is a tool. You want something. You're figuring out how to get Python to give it to you. The friction in this phase is entirely between you and the language. The shift that ends this phase, realizing that you also need Python to communicate to the next engineer what you wanted. Code is not just instructions for a computer, it's a message to a human. The moment that becomes real, not just conceptually but viscerally, is when year 1 Python ends. Year 2-5. I need to write Python that doesn't embarrass me in a year. This is a growth mindset and a useful one, but it's still centered on you. The code you're writing in year 3 is better than year 1. You can see that, you're proud of it. The shift that ends this phase, writing Python that doesn't embarrass the team in a year, not your code, our code The moment ownership becomes collective, the moment you feel personally responsible for a code base you share, is when year 2 Python ends. Year 58. I need to write Python that the next engineer can extend. This is the senior shift, not code that works, code that invites improvement, code with the right extension points, code that tells the next engineer where to add things and where not to, through structure alone, not through comments. The engineers who make this shift early reach senior before their peers. The engineers who never quite make it plateau indefinitely, writing good code that no one wants to touch. Year 8 to 12. I need to write Python that the next team can maintain. This is the staff shift and it's organizational, not technical. At this level, you are not writing for one engineer. You are writing for a team that will change composition over 3 years. Some of the people who will maintain this code haven't been hired yet. That changes everything about how you make decisions. Fewer clever tricks, more explicit structure, more documentation of why, not just what. More attention to what happens to this code when the person who wrote it leaves. Year 12 to 16. I need to write Python that the next generation can learn from. At principal level, the code becomes instructional, not intentionally. But inevitably, the code that principal engineers write becomes the example that junior engineers look at when they're trying to understand how to do something. That responsibility for whether the examples are good ones is one the engineers at this level take seriously. It shapes which patterns they use, which they avoid, and which ones they document their reasoning on. Year 16, 20 plus. Python is the medium. The craft is what matters. At 20 years, the language is not the point anymore. The point is the idea you're expressing through it, the problem you're solving, the system you're designing, the engineer you're mentoring, the community you're building. Python is the medium. The craft is everything that happens through it. The engineers who reach this level don't talk about Python features. They talk about what Python makes possible for them, for their teams, and for the people who use what they build. That's a relationship with a tool that most engineers never develop, and it's worth understanding not as an aspiration but as a destination, even if you're at year 2. Acknowledge the complexity. Take a clear position. Let me address the question that comes up every year and this year more urgently than ever. Is Python still the right language to invest in, or is it being replaced? Every year since about 2018, someone has declared that Python's days are numbered. Rust is faster, Golang is simpler, Julia is better for ML, JavaScript has Node, TypeScript is taking backend. Here is what I believe after 20 interviews with engineers who have spent a combined total of more than 200 years in this language. Python is not going to be replaced in the next decade. And here's the honest reason why. Python's dominance is not technical, it's social. It is the language of the scientific community. It is the language of machine learning research. It is the language of data engineering at every scale. It is the language of AI product development. Those communities are not going to switch to Rust. Not because Rust isn't better at certain things, it is. But because the cost of switching is not just a language cost, it's an ecosystem cost, a tooling cost, a hiring cost, and a cultural cost. Python wins the next decade not by being the best language for everything, but by being the language that the communities that matter most have already built their world in. What is changing, and what the engineers I talk to are paying attention to? The no-GIL future. CPython Python 3.13 experimental, aiming for Python 3 0.14 Python 3.15 stable. If the GIL is removed or made optional, the ceiling on Python performance for CPU-bound parallel work rises dramatically. The engineers who understand threading and the GIL today will be the ones who can use this when it lands. Faster CPython. The Faster CPython project, Shannon, Guido, and others, has already delivered 10-60% speedups across Python 3.11, Python 3.12, Python 3.13. Python's performance criticism is becoming less valid every release. Python for WebAssembly. Pio died running Python in the browser at near native speed. The language's domain is expanding, not contracting. AI-assisted Python development. This is real and it's significant. The engineers I talk to who are most effective with AI coding tools are the ones with the deepest Python foundations. Not because AI tools replace that foundation, but because you need the foundation to evaluate what the tool gives you. AI tools write plausible Python. Experienced engineers know whether it's correct Python. The engineers who will thrive in the next decade of Python are the ones who invest in depth now, before AI tools make shallow. Python feel sufficient and stop them from going further. Surface level Python is about to become a commodity. Deep Python, the kind that can design systems, evaluate AI output, build the tools everyone else uses, that is becoming more valuable, not less. Show clips or steals from interviews as you mentioned them. Here's what's in the full series: 20 full-length conversations, each one 45 to 60 minutes, one engineer per year of experience, all of them talking about the same language from completely different places in their career. Episode 1, Year 1, Learning Python versus learning to program in Python. The distinction that most tutorials miss entirely. A one-year engineer describes learning Python correctly and the 3 things she wishes someone had told her in month 1 that would have saved 6 months of building habits she had to unlearn. We also cover how to evaluate Python learning resources without getting lost in tutorial hell, and the one project type that builds real Python skills faster than anything else. Episode 2, Year 2, Writing code that other people can read. The first professional milestone nobody warns you about. This engineer shipped his first module into a shared code base. His senior's feedback changed how he thought about code for the next 8 years. We cover naming, documentation, module design, and why readability is a technical skill, not a soft one. Episode 3, Year 3, The Intermediate Plateau. How to get unstuck. The most common question from Python engineers at this level. The syntax. You can solve problems, you don't know what good looks like. This episode diagnoses the plateau and maps the path out. We go deep on reading open source Python, the projects that build taste, and how this engineer went from it works to it's good. Episode 4, Year 4, Testing, Types, and the professionalism gap, the skills that transform a capable Python engineer into a reliable one. PyTest in depth, Mypy from scratch, the discipline of code review. This engineer describes the moment she realized that untestable code and untyped code are design problems, not just quality issues. Episode 5, Year 5, Decorators, Generators, and the Python Data Model. The intermediate to senior technical bridge, taught properly, not as tricks as tools with clear use cases. This engineer walks through the Python data model with the depth that tutorials never give it, and explains why understanding it changed how he designs every class he's written since. Episode 6, Year 6, Async Python. When, why, and what goes wrong. The most misused feature in intermediate Python. This episode is the async education that most engineers wish they'd gotten before they wired async into something that didn't need it. We cover the event loop the difference between concurrency and parallelism, the patterns that make async Python slower than sync, and the use cases where async is genuinely the right answer. Episode 7, Year 7 Performance. Profiling, optimizing, and knowing when to stop. Nobody profiles before they optimize. Everyone should. This engineer broke production with a performance improvement in year 4. Here's what she learned and the profiling discipline she's followed ever since. We cover C profile, line profiler, PI spy, memory profiler, and the judgment to know when the bottleneck is the algorithm, when it's the implementation, and when it's the architecture. Episode 8, Year 8, the type system, using Mypy and Pyrite in production. Full type coverage in a large Python codebase is hard. This engineer has done it twice in different organizations. The technical depth here goes beyond tutorials. Generic, protocol, type var, param spec, overload, and the patterns that make a typed Python codebase a pleasure to work in rather than a constant fight with the type check. Episode 9. Year 9, Designing Python. AP is that people love to use the most underrated skill in Python engineering, not writing libraries, designing APIs. This engineer has built 2 open source Python libraries with combined downloads in the tens of millions. He talks about the design decisions and the mistakes that shape them, and the thing he wishes he'd understood about API design from the beginning. The API is a promise. Design it like one. Episode 10, Year 10, Staff Engineering in Python. What owning a codebase means, the milestone most engineers have heard of and few understand. A 10-year Python engineer describes the transition from senior to staff. What changed in how she thought, what changed in what she owned, and the decision that defined her first year at staff level. We cover codebase level design, dependency governance, Python version strategy, and what it means to be responsible for code you didn't write. Episode 11, Year 11, CPython Internals. What you need to know, not a CPython deep dive for its own sake. A practical guide to the internals that matter for production. Python engineering. How the interpreter works. What bytecode is, what the GIL prevents, and what it doesn't. How reference counting works, and why it matters for memory efficient design. This engineer reads CPython source for fun. Here's what's useful. Episode 12. Year 12, Building Python Tools that other engineers use. CL is code generation tools, linters, formatters, test runners, the internal tooling that staff and principal engineers build that makes everyone around them faster without anyone fully understanding why. This episode is about the meta engineering layer, the Python that builds the environment that other Python is written in. Episode 13, Year 13, Python for AI infrastructure, the highest leverage Python. Right now, the intersection of Python mastery and AI engineering. What does Python engineering look like inside a frontier AI lab? How is it different from Python in a web startup or a data team? This engineer has been on the Python side of AI infrastructure at scale. The work, the performance constraints, the engineering culture, all of it, honestly. Episode 14, Year 14, Managing Python at Scale. Monorepos, log files, and Team Python. The organizational Python problems that don't appear in tutorials. How do you manage Python dependencies across 30 services? How do you make a Python version upgrade smooth for a team of 40 engineers? How do you write internal Python style guides that engineers follow? This engineer has solved all three, not perfectly, but honestly. Episode 15, Year 15, the principal Python engineer. Influence without authority. At principal level, your influence is not positional, it's reputational. This engineer describes how she shapes Python practice inside a large organization without having anyone directly report to her. Through code review, through internal writing, through the examples she sets in the code base, through being the engineer that other engineers want to work like. Episode 16, Year 16, Contributing to CPython. What it takes, not a how to on submitting a PR. An honest account of what it costs and what it gives back. The review process, the culture of the CPython core team, the work that never makes it in, and why that's part of the process. And the thing about contributing to a language used by millions of people that this engineer didn't expect to feel. Episode 17, Year 17, Python Communities. PyCon, PSF, and why they matter. The social infrastructure of Python. What PyCon is not the talks, the community, the PSF, and what it does for the language. How local Python user groups create the distributed mentorship network that pulls new engineers into real Python practice faster than any tutorial. This engineer has organized a PyCon. Here's what that revealed about the community. Episode 18, Year 18, Teaching Python. What it reveals about what the engineers who teach Python deepest understand it best. This engineer has taught Python in 5 formats: university courses, corporate training, open source documentation, conference talks, and one-on-one mentorship. What each format reveals about your own gaps, and the Python concept that every engineer thinks they understand until they try to teach it. Episode 19, Year 19, Reflecting on a Python career. What compounded and what didn't, near the end of a 20-year arc. This engineer looks back not nostalgically but analytically. What mattered? What didn't? What did she wish she'd prioritized earlier? What did she spend too long on? What is she still learning? This episode is for every engineer who wants a 20-year perspective while they still have time to use it. Episode 20, Year 20, Python at its fullest expression. The final conversation. A 20-year Python engineer, core contributor, PEP author, community builder talks about what the language has become, what it cost to master, and what it still has to teach him. Not a victory lap. A craftsperson's honest accounting of a career spent in one language. And what he'd say to the engineer who's at year 1 right now reading this description. 20 episodes, 20 years, one language. Start at episode 1 if you're beginning. Jump to episode 5 if you are intermediate and stuck. Go long to episode 10 if you are aiming at staff. Watch episode 20 regardless of where you are. It will change what you are optimizing for. Here's what I'll leave you with. When I started this series, I thought I was making a Python career guide. 20 interviews later, I realized I'd made something different. I had documented what it looks like to commit to a craft. Not to a language feature, not to a framework, not to a domain, to a craft. To the sustained, patient, decade-long project of learning to express ideas in code with increasing clarity, increasing reliability, and increasing care for the people who will use and maintain and learn from what you build. Python happened to be the medium, but the thing that all 20 engineers shared, the thing that connected year 1 to year 20 was not the language, it was the orientation. They cared not about being impressive, about being useful, not about knowing the most advanced features, about using the right ones, not about shipping fast, about shipping something worth shipping. Almost every one of them said some version of the same thing when I asked what they tell themselves at Year 1. Read more code than you write. Understand it before you judge it. And don't rush the parts that are supposed to be slow. That's what this series is. 20 years of Python mapped honestly so you don't have to figure it all out alone. Subscribe if this is the content you want more of. Drop a comment. Tell me what year of Python you're at right now. And tell me the one Python concept you're working to genuinely understand, not just use. I read every single one. And if this gave you something useful, share it with one engineer who's trying to figure out where they are on this map. That's enough. Let's get into it.